Hi, my name is Bill Corwin. I'm with the Advanced Reactor Technologies Office of Department of Energy, Office of Nuclear Energy, and I'd like to talk today about a topic, integrated research project as part of the overall Nuclear Energy University program dealing with codification of compact heat exchanger usage for nuclear systems. For those of you who may have listened to my talk half an hour or so ago on other individual NEIPs, I apologize. Some of the introductory slides are the same. For those of you who didn't, well, guess what? You get to hear them now. Structural materials are clearly critical for advanced nuclear reactors, and for that reason, Department of Energy is got activities to develop and qualify advanced structural materials that are critical to the design and development of some of the advanced nuclear systems that we are developing. We are focusing on high temperature and very high temperature gas-cooled reactors and sodium fast reactors, but are also looking at salt-cooled high temperature reactors, both molten salt, those in which the fuel is dissolved in the salt coolant, and fluoride high temperature salt-cooled reactors which have solid fuel in them, as well as lead and lead bismuth cooled fast reactors. Now, the structural materials in these systems have to perform over their entire design lifetimes for the various components, things like pressure boundaries, reactor internals, heat transfer components, etc. Therefore, the Advanced Reactor Technologies program is supporting R&D on the performance of those structural materials for the long times, high operating temperatures, and environments in which they are required to perform. These activities support the overall advanced reactor development detailed in the R&D plan roadmap put to Congress in 2010, specifically the topics dealing with developing improvements for the affordability of new reactors and to develop sustainable nuclear fuel cycles. The activities incorporated in the Advanced Reactor Technology Program include activities on the development and qualification of graphite, improved high temperature alloys, and ceramic composites. But in addition to that, it also deals with a lot of the design rules for using those materials, specifically with regard to the ASME code. A couple of the systems that are examples of the advanced reactors that these are applicable for include the AFR 100, a fast sodium cooled reactor system, 250 megawatt thermal, 30-year core life, 60-year total life, and AREVA's high temperature reactor, 750C, moderately restrained for a high temperature gas cooled reactor. They can conceivably go up to as high as 9 or 950. 625 megawatt thermal with a steam generator and a 60-year plant life. Other systems, as I mentioned, also involve high temperature reactors cooled by liquid lead and liquid salt. Now, these various and assorted reactors may very well use advanced energy conversion systems that incorporate compact heat exchangers. In particular, Brayton cycle systems based on supercritical CO2 have been shown to improve thermal efficiency and operating economy for some of these advanced reactor systems. Compact, high efficiency SCO2 recompression closed Brayton cycles that operate at moderately high temperature, about 550 C, and 20 megapascal are being developed and demonstrated at the Sandia National Labs as part of the ART program. Using a compact heat exchanger to couple a sodium fast reactor plant to a Brayton cycle energy conversion system for electrical production, instead of using a steam generator, has been shown to minimize reactor and plant footprint and reduce capital costs, for instance, in the AFR 100 system. It's also possible to use such a compact heat exchanger to couple Brayton cycles to salt-cooled or lead bismuth cooled systems at temperatures up to 750 C or so, again with associated reduction in capital costs and reactor footprints. For even higher temperature systems, such as the very high temperature reactor, 750 up to as high as 9 or 950, it's possible to use compact heat exchangers to transfer heat between the primary and secondary heat transport systems, helium, instead of using traditional tube and shell type intermediate heat exchangers, thereby reducing capital cost in such systems. This would be used primarily for transferring heat for process heat applications, but could conceivably be used as an intermediate step for a helium Brayton cycle as well. Temperatures are much higher in this case, but the pressure differential across the compact heat exchanger would be quite low, even though the total pressure would still be quite high. So the challenges would be similar but different for this type of a system. Compact heat exchangers are even critical to some of the advanced integral light water reactor designs, such as the Integral Inherently Safe Light Water Reactor System, developed as part of a recent IRP performed at Georgia Tech, wherein all of the components for the primary circuit are contained within the reactor pressure vessel, things such as the core and the internals, control rods, etc. But this approach requires a high power density compact heat exchanger located within the reactor pressure vessel to transfer hot water from the vessel outside the vessel to a steam flashing drum. And you cannot do this with a shell and tube type of system because there's not enough room for it in the system. So there's a lot of applicability for these compact heat exchangers in advanced reactor systems. So what kind of compact heat exchangers are we talking about? Some of the more common varieties are shown here on the slide. There's the diffusion bonded microchannel, wherein there is a series of thin plates or shims which have been chemically etched and then diffusion bonded together. It gives good fluid flow distribution channels and is quite stout, good for high pressure systems. On the other hand, you have diffusion bonded or brazed fin compact heat exchangers where there's corrugated plate fins. They're sandwiched between two flat plates or shims. This is more efficient use of materials and allows for larger flow passages and lower flow resistances. And it's even possible to combine these into a composite type. And this is one of the types of heat exchangers that's been proposed for supercritical CO2 service, where the high pressure supercritical CO2 would be contained within the microchannels, whereas the lower pressure sodium or other fluid might be contained within the plate fin configuration. Now, what's the challenge with these things? Well, there's a lot of challenges with these things. Compact heat exchangers have very complex geometries, both at the micro scale and the macro scale. There's complex arrangements of flow channels and distribution manifolds, both within the individual passages and at the header systems. There's sharp corners. There's very significant stress concentrations which cause stress redistribution from pressure and thermal stresses that have to be accounted for. And the current design process within ASME is challenging. The only rules that exist for design and construction of compact heat exchangers at this point are contained within Section 8 of ASME code. This is the portion of ASME code that deals with rules for construction of pressure vessels, not the nuclear construction. And this provides for microchannel sizing rules based on staid rectangular vessels, such as shown in the upper right corner of the slide. These rules do not consider thermal or cyclic loading, and they do not adequately address elevated temperature bending or stress restrained redistribution due to creep. They simply are not required for Section 8. On the other hand, Section 3, the Nuclear Construction Code, requires consideration of thermal stresses and cyclic loading based on stress classification. It's recognized that thermal stresses are very important for allowable cyclic life, particularly at these elevated temperatures. And the stress classification required by Section 3 requires deconstruction of using finite element results into primary, secondary, and peak stresses. And you can't do that at the sharp corners that exist within these compact heat exchangers. It's just simply incompatible with the methods that currently exist within ASME Section 3, Division 5. Moreover, the requirements for fabrication are not compatible with those that are in Section 3. The requirements for diffusion bonding related to Section 8 are covered in the mandatory Appendix 42 in Division 1 of Section 8. These are similar to, but not identical to, those that would be covered under Section 9, which is referenced by Section 3. Moreover, the design and fabrication rules in Section 8 allow only for 3 varieties of stainless steel, 304, 316, and both of those are the L variety, and 2205. And none of those materials are those that are allowed in for nuclear construction. Bimetallic bond joints are not allowed. That may or may not be a limitation, but it's not allowed even in Section 8. And the vessels, even under Section 8 rules, cannot be used for lethal service, that being for any material that is considered a lethal substance. This would be a serious limitation for something such as a beryllium-containing salt. So even under Section 8, if they were sufficient, we couldn't do the Section 3 construction with those. It's possible to do a U stamp, which is the kind of stamp the code puts on for Section 8 vessels, but it's not possible to put on an N stamp, which is required for nuclear construction, because we simply don't have the rules for that. Establishing the rules and procedures for Section 3 need to be developed. So, what do we need to have done, and done within this IRP? Well, we need to have additional welding development for the diffusion bonding process that is required to fabricate these things, that is done to allow the rules to be developed according to Section 3 requirements. We need to have the development of design rules and design analysis methods for compact heat exchangers in nuclear service be established. However, I will point out that is outside the scope of this IRP. That is being handled specifically within 3 current NEUP awards, but there will need to be a strong, close collaboration between the results of those 3 projects which are in process to understand what the results of those things are, because it's going to be required to design and fabricate representative sections of compact heat exchangers and or subscale models of those things, which can be then used for testing to generate data to validate those design rules and analysis methods that are being generated by those NEUP projects. It's going to be necessary to develop innovative methods and technologies to be able to do post-construction examination and testing of the compact heat exchangers. Those do not exist right now. It's going to be required to examine the potential for how do we deal with fouling of the microchannels that may very well occur in nuclear service based on the service experience that's coming out of the Section 8 vessels. These Section 8 vessels are widely in use in petrochemical and fossil energy. There's a lot of them that are out there, so we need to take a look at the experience that those things have generated heretofore, look at methods for cleaning the microchannels and testing those things. And lastly, we need to develop innovative in-service inspection methodologies that are applicable to compact heat exchangers in nuclear service. How to address inspection for service life, for cloggage, leakage, other conditions that are adverse to performance. We know we can't develop itty-bitty little eddy current probes to go down every single channel like we're doing with steam generators these days. So do you do overpressure tests? Do you do leak tests? What do you do to develop the rules that are required by Section 11 on in-service inspection for nuclear parts? But and that is not required that all of those rules get developed. We're focusing on the construction aspect of this, but if you don't construct it for inspectability, then you're shooting yourself in the foot. So that needs to be considered at this point, such that the design and construction process takes into consideration what is going to be needed for an inspection in service. All right, interaction and collaboration with this. Certainly need to interact with the ongoing NEUPs that are developing the compact heat exchanger design rules and design analysis methodologies, because those are the ones that are going to need to be evaluated in the testing. We strongly encourage collaboration with ASME subject experts who are familiar with the lack of rules and the complex subject matter that goes on in this, and we strongly encourage interactions with existing compact heat exchanger manufacturers. We consider that very valuable to the overall activity. And I've included a reference at the bottom of this, which is probably the most complete current reference we have. It was put out a couple of years ago, a report by Jim Nestel of NPR and Sam Sham, talking about what is known with regard to code considerations, deficiencies, areas that need development and whatnot. It's available at the URL that is included in that reference, and I strongly recommend anybody who is considering putting in a proposal on this to take a thorough read-through of that document. Points of contact on this, I am the point of contact as a Fed, and Sam Sham at the Argonne National Laboratory is the point of contact for technical questions. Sam is integrally involved with the code aspects of this and will be very capable at answering questions on this. He's also one of the authors of the preceding document I talked about. So with that, I'll be happy to take questions.
Bill, we do have Sam on the line. Sam, are you there?
Yes, I'm here. Can you hear me?
Sam, are you there?
I'm here. Can you hear me?
Yes, we can hear you.
Okay,
Excellent.
thank you.
Okay, we'll start with a question from RC3. Somebody submitted this in the past half hour, so we'll clear that one out and then we'll start on the IRP questions. For RC3, does commercial software for analyzing and optimizing, like finite element codes, is that of interest?
RC3, the topic addressed at the previous discussion that I had up here, was on degradation and evaluation methods for predicting degradation and failure in 6-SiC composites. If there are commercial finite element codes that can be used in conjunction with the data that's needed to predict those, the performance of 6-SiC, that would be fine. However, we're not looking merely to exercise commercial codes. We're looking at the information that's required to predict the behavior of the 6-SiC. So as a tool, it would be fine, but that's probably the limitations of commercial software in this case.
Now on to the IRP. Is it expected to address all 6 areas in one proposal or a certain subset?
No, it's expected to address all of the areas. This is an IRP, an integrated research project, and that's one of the reasons why we wanted to get a team of people to take a look at this as a total project. The only piece not to be developed, and we laid that out specifically, was the development of the design rules. Those are being done under the 3 existing NEUPs, but close collaboration with those parties would be expected.
Regarding those existing NEUPs, will there work scopes or reports be made available so that these efforts can be dovetailed into this current IRP?
Yes, those began this past year, so those are works in progress. But if anyone is interested in the information from those, they can contact me or Sam, and we will make available what is available from those to proposers.
And one-page abstracts of those, all 3 of those awards are on NEUP.gov under 2016 funded R&D awards. If collaboration with DOE labs is essential, is that the same for industry?
Actually, I don't believe I said collaboration with DOE labs was essential. What I said was collaboration with the NEUP projects was essential. I said a good resource would be to look at the report that was published last year, and the reference is given right there. It's an ORNL report. The principal author on that was Jim Nestel from NPR and Associates. Sam Sham also contributed to that, but it's not principally a work from the National Lab. It's more from a code perspective than the National Lab perspective. Sam, if you have additional comments to make on that, please jump right in there.
Yes, as what is shown on the screen in Bill's slide, that really we're looking at sort of interaction, obviously, as Bill pointed out, with the ongoing NUP projects, and also more importantly, in terms of some of those sort of either in-service inspections or post-construction examinations. So collaborations to bring some of the ASME subject matter experts into your team will be highly encouraged. And also that there are a number of compact heat exchanger manufacturers. So those are sort of these three pieces are really an integral part of this IRP to sort of bring all of these different parties to bear to make the project a success.